Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 52 today and we are discussing about adhesion measurement using a thin adhesive film bonded to a rigid substrate. And these are the list of references, and as I told you in the last lecture, we are discussing this subject from this particular paper of mine, and then we will go to study another interesting topic which is about peeling off a biomimetically patterned thin elastic film. So, in the last lecture I described to you this particular experiment in which you have this rigid substrate, on this rigid substrate an elastic adhesive film that is bonded, and then from the top we bring in contact this flexible adherent plate. So, this plate comes in contact, but it does not come in contact completely. We put a spacer over here, and as a result this plate, flexible plate, that bends, and because of the balance of forces which we described last lecture, that it comes at a equilibrium distance from this spacer which is given by this A. So, we measure this A as a function of this delta over here, and then we do the calculations. So, I have not presented the complete calculation yet, but before I do that, today I will like to show you one experiment. Friends, here is a elastic film which is bonded to this glass plate, as you can see. So, it looks completely flat from the top, and so we have casted this particular film on this glass plate itself. And now I will bring a flexible adherent plate. So, this is a flexible adherent glass plate. Normally this is a cover slip. So, this is the way we do the experiments in the lab, that is what I am going to show you. So, this is about, let us say, 150 to 200 micron thick. This is called a flexible cover slip, which is used in biology lab or in chemical engineering lab, and then this particular plate is brought in contact, but it is not contacted directly. We place a spacer. So, the spacer is a thin strip. So, normally this filler gauges which is used, for example, we can use different thickness. So, for example, that this particular filler gauge, this is about 90 micron over here. So, we put that filler gauge over here on this film, little bit attach it, okay, does not matter, and then we take this flexible plate and bring it in contact, place it on this film like this, okay, and then you use a little maybe solid something to put it in contact. So, the plate comes in complete contact, but not completely to the up to this particular spacer. So, it stops somewhere here, you will not be able to see it, I am sure, because in microscope only we need to see it clearly, but this is the way this works. And so, this geometry that I am showing is very similar to, or the basically presented in this figure in my slides. So, this particular flexible plate, okay, that we have it here, that bends, and this particular plate bends, and suppose if we increase this thickness of this plate, then it will bend little more, but you can see that the extent of bending is actually too small, okay. So, therefore, we can use this small bending approximations in our calculations. So, now we can change this spacer and use different spacer height, and so that the contact the distance of this contact line from this spacer, that is quantity called A in my graph slide there, okay, this varies. So, we measure this spacer height and this A, and then do the rest of the calculation. So, here this is the geometry I just described to you in the experiment, and today I will like to continue this further. So, if you remember, in the last lecture we had derived the expression for the deformation field inside this elastic adhesive, and then we described also the sigma zz, that is the normal stress on this particular film on the surface of the film, and that is given by actually is equal to minus of the pressure, okay, that is there. So, this is given by this expression that comes out to be. So, you can see that this normal stress, that is also a sinusoidal function, okay, oscillatory function, and it has an amplitude that decreases exponentially, okay. It is the result is same as the displacements. So, here I have plotted the vertical displacement and the normal stress. So, the vertical displacement is this axis, right. This is the axis, and you can see that it starts from here, this is maximum over here. So, this is at x is equal to 0. What it means is that x is equal to 0 means this particular point, right. So, at x is equal to 0, this is here, and x tends to infinity is over here, okay. This is at minus infinity, something like that. So, now in this region, okay, the deformation of this plate, that is tensile, of course not plate, I mean the plate is up. So, the film is tensile over here, and then this becomes compressive. So, it is actually goes down little bit, and then once again tensile, and like that. So, this oscillation goes on and with a decreasing amplitude, and the stress also like that becomes maximum over here. So, this is the stress as a function of distance plot, and this is a down dimensional. So, this has been made dimensionless by this quantity. So, d here is flexural rigidity, you know that, and K inverse is has a dimension of a length. So, here this also becomes this stress also normal, that is also oscillatory. So, what is the wavelength of the oscillation? So, that can be seen from here, okay, the wavelength, and it seems that it comes out to be, this lambda comes out to be close to about 5.6 K inverse, okay. So, that is the way this works. So, with this result and the displacement fields and all that, we can actually find out the energy of the system. So, energy of the system will consist of the elastic energy of the film. Now, the elastic energy per unit volume of the film has been derived like this. So, this expression you must have seen it earlier, presented it, and so we can find out the actual expression. So, here this is half, and then this is xx, it is the normal stress in the x direction, and zz in the stress that is in the z direction, which acts on a plane perpendicular to the z axis, right. So, here we can use this u of x, okay, plus w z is equal to 0, that is the continuity or incompressibility relation. So, remember that our film is incompressible, that is what we have considered. So, therefore, here w z is equal to minus of ux. So, these are the strains. So, here therefore, we can write it here xx minus zz, and let us say this is ux, okay, and plus this is 2 zx and ezx. So, that is the energy due to the shear strain, okay. So, these are the energy due to the normal strains, here it is due to the shear stress and shear strain. Now, what it so happens that we are considering this incompressible material. So, therefore, incompressible material. So, therefore, the stress field inside the film is stress field, okay, in the film is hydrostatic. Therefore, this quantity xx minus zz, that will be equal to 0. That means these are equal because hydrostatic. So, that is why this is equal to 0. So, therefore, this elastic energy in the film, that is actually equal to half into 2 into zx. So, zx is equal to 2 mu, and ezx, that is equal to half of, this is del u by del z plus del w by del x, like that. So, half, this is 2 mu. So, finally, it will come out to be, so this is zx and ezx. So, ezx is another half, right. So, del u by del z plus del w by del x, that is what it should be. So, this quantity, this comes from over here, and this part that comes from this zx part. So, this is equal to zx. Okay. So, from here we get this 2 cancelled, this 2 gets cancelled. So, you get mu here and 2 here, and del u by del z plus del w by del x whole square, like that. So, the elastic energy is given by this particular expression, and then we have the expression for bending energy. So, bending energy is something like this. I told you earlier that d by 2 into curvature square. So, curvature of the plate will be given by del zeta by del x. So, this is xi here, okay, because this is curvature. So, del square xi by del x square, that is the curvature here, and d by 2, and now you have to integrate it from x from minus infinity to a, Okay. So, in between this xi has got from minus infinity to 0, it has got one expression, and from 0 to 8 this is another expression, right. So, that we have gone through in the last lecture, that we have shown it. By the way, this here also we have to integrate it. So, let me integrate it over here. So, it will be the total energy, this will be here from 0 to h, and then here it is minus infinity to 0. Okay. This is mu by 2 and del u by del z plus del w by del x whole square and dx dz, because this quantity that we had earlier, this is per unit volume. So, you need to integrate it over the whole volume of this film, that is all you need to do. So, therefore, we have this quantity. So, this is per unit volume. So, you have to multiply, you have to integrate it over the volume of this material. So, now this becomes this energy, this is energy per unit width of the film. Okay. So, whatever that energy you are calculating is per unit width of the film. Remember that, width of the film, right, this is in denominator. So, this was the curvatures into square. So, here also you are going to multiply by dx over here, and then the surface energy, that is very clear, that is work of adhesion into, or let us say W only, and into A, right, because in this particular case geometry, this portion. So, this portion, as you can see, so this is A. So, these are the portions, these portions have been opened up because of this spacer, and so therefore, the work of adhesion is W into A. Again this is also energy per unit width of the film, right. So, you remember that. So, this is also per unit width, this is also per unit width. So, now we add up all these energies. So, the pi total, okay, that will be equal to this pi elastic plus pi bending energy that we just obtained plus pi surface energies. Okay. So, we do all that. So, that becomes the total energy, and the total energy is minimized with respect to this quantity crack length, we call it A. Okay. So, we get the expression of the total energy in terms of this A, right, for a given film thickness and modulus of the film and like that, and the flexuality D. Okay. So, minimize, okay, the total pi total with respect to A, okay, for given d flexural rigidity of the plate, mu elastic modulus of the film and film thickness. So, we do that, and so therefore, so d of pi total by d of A, that is equal to 0. So, here all these expressions have been said. So, finally, so del u by del x del z you have to calculate. Okay, let us do that. So, here u expression we have already obtained in the film. So, del u by del z over here is 6 by k h cube. So, it is z square there. So, it is 2 z and minus z of h. So, it is h there. So, z square minus z is, yeah. So, it is like that, and this is f dash and rest of the things whatever is there. Then you have del w by del x. So, here this part remains z square by 3h minus 2 z, right, and this is h cube and this is f dash. Now, we need to find out the derivation with respect to x here. So, here let us do that. So, it is k by 2 e to the power k x by 2, and then whatever is there, there is no change over here, plus let us write now e to the power k x by 2, and then let me do it over here. So, it is a k, so a k into k by 2. So, it is k by 2 e to the power k x by 2 plus this is 3 a k plus 2 by square root of 3, and this is sin here sin k. So, it is root 3 k by 2, and this becomes cos. So, it is root 3 k x by 2 plus this is a k plus 2, and then it is root 3 k by 2, and this is cos here should be minus. So, let me do it correctly, minus over here, minus, and this is sine of root 3 k x by 2, like that. So, here this is what we have, and this is the bigger bracket, this is the, yeah, so this is correct. So, we need to now collate all the terms. So, z square by 3 h minus 2 z by h cube by f dash into f dash, and then let us say that we take out k by 2. So, k by 2 we can take out, and let us say I take out e to the power kx by 2 as well. So, e to the power kx by 2, right, and so therefore, I am left with here a k into this is e to the power kx by 2 plus this is 3 a k plus 2 by root 3 and sine of root 3 kx by 2, okay, plus this is a k plus 2, okay, into cos of root 3 kx by 2. So, this is the first part, and the second part plus, okay, I have taken out k by 2 and e to the power kx by 2. So, I am left with a k into e to the power kx by 2 over here, and then plus I am left with, so k by 2 has been taken out and e to the power kx by 2, so root 3 here. So, root 3 gets cancelled. So, it will be 3 a k plus 2 and cos of root 3 kx by 2, and then minus again over here k by 2 is gone. So, it is root 3, it is a k plus 2 and sine of root 3 kx by 2. Okay, so now we have to just do the rest. So, this let us say this is outside this bracket, this whole part, and over here. So, it is 2 a k e to the power k x by 2, okay, and then plus then the cos terms. So, cos of root 3 a k plus 2 plus cos of this over here. So, it is 4 a k plus 4, cos of root 3 k x by 2, and then for the sine we will have plus over here, this is 1 by root 3 and this is minus root 3. So, minus minus 3 will be here. So, here in the denominator root 3 should be there, and this is 3 a k minus 3 a k, it is gone. So, it is minus 3 minus 6, 2 minus 6 is minus 4, I guess. So, it is like that. Here this is the way it comes out. One can actually this k by 2. So, I have divided k by 2 everywhere, that is fine then. So, I think I have done it okay. So, finally, we will get this result. So, this is for the du by dz plus dw by dx. So, now you add it up, okay, and add it up, and then you find out the integration of that, and you, as I said, minimize the whole total energy. This is the total energy, by the way, this is actually total energy that you minimize with respect to A, keeping all the other terms constant, okay, put it 0. Then we use this particular limit that kh small. So, as you saw that the film that I showed you, that was quite large with respect to h. So, kh was smaller than 1 or was smaller than 1. In that limit we can get this work of adhesion W as this particular expression over here. So, 9 d delta square by 2 a to the power 4 g of a k. So, this is a function of a k that we get. This function can be obtained something like this. Okay, the calculation is quite involved. If you wish, you can use this Mathematica software, or you can use your own calculation also, but it comes out quite nicely and like that. So, this is the expression that you get, work of adhesion. So, in the work of adhesion, you see the term d is the flexural rigidity of the plate that is there, and you have got the delta. What is delta is the extent to which this plate is moved up, okay, the flexible lifted, that is delta over here, and 2 a to the power 4 and g and 2 g a function of a k, a and k inverse. So, k inverse over here, remember this is equal to dh cube by 12 mu whole to the power 1 upon 6, like that. So, this particular work of adhesion expression, this has the effect of all the terms, okay, the flexural rigidity, a, delta, and then this h thickness over here, and modulus also. So, it has the effect of all the terms, and so what you can do is we can do the experiment with different values of this delta, and correspondingly we measure a. So, delta as a function of a, right. We need to rescale it somewhat, and I will show you how to do that, and then we can get from that data, analyzing the data, the quantity work of adhesion, okay, we can get that. So, there is one point that needs to be mentioned here is that this result that you have gotten, that in this case if g of a k, okay, is equal to 1, if we put, that means we are peeling off or lifting off of a rigid plate. So, that means suppose we have this film over here, okay, from which you are peeling off, and this particular flexible plate, right. So this is very similar to, if you know, if you have seen this mica sheets, when mica sheets are peeled off from one after one layer separated, then the situation is very similar to this. So there is no deformation over here, right, and so there it, in a sense, this peeling off is being done from a rigid substrate like that, no deformation. So this G of AK is equal to 1, that corresponds to that situation, and in that situation, for obviously W is equal to 9d and delta square 2a to the power 4, okay. And this result was obtained in 1930s by Obraimov. This is called Obraimov result, Obreimov's results, okay. So the result that you get show here, that in the limit that of a rigid plate, okay, a rigid adhesive film, this result matches with Obraimov derivation, and this Obreimov's paper got published in 1930, right, in Royal Society, London. You can see this paper if you are interested. Now what I will like to do is to show that how to use this equation to find out the work of adhesion. That's why I like to do that. So here we rescale it somewhat. So 9d delta square, let us multiply and divide by k to the power 4 to make this particular term dimensionless. Then it is G of AK like this, and let us write it like this now. Let us say write it W, work of adhesion millijoule per meter square. Let us try to normalize it by using this quantity called gamma. So the gamma is the surface energy of the film. So let us say this is surface energy of the adhesive film. So we want to write in non-dimensionless quantity. So we need a dimensionless characteristic quantity for work of adhesion to normalize it. So gamma is a right candidate. So let us say you divide it by gamma here. So it becomes 9d delta square. This is k to the power 4 and 2 ak whole to the power 4 and G of ak over here. Now let us say that I multiplied, we are divided by 12 here. So it becomes 12, and I will show you why I am doing that. This is okay, we can do that. So here this quantity now will be 3 and 4 here. So it is 4 here. So it 8. So it is 3 by 8, and this is delta square k to the power 4 by ak whole to the power 4 and G of ak like this. So now I will like to write it like this. Yeah, so d k square w delta square by you have to divide it by gamma also here. So the gamma we should be here also. So gamma has to be here also. So here what will I have now? Oh, sorry, d delta square. So d also has to be there. D delta square k4, right? So here like this. Now we can further write it. So d delta d k4 to the power delta square by gamma, okay, that can be represent square root of that, can be written something like this, right. So this is just one more step. So here therefore what we will have is that we can measure this, as I said that for different delta I can measure the A and then obtain this x and y coordinate over here. So let us say that we calculate this particular term 8 of ak to the power 4 divided by 3 G of ak, and then we do the square root of that, and then here I have d k4 delta square by gamma to the power square root. So I plot this quantity, I write it as function 1 of ak and this quantity like that. Now, so what if I plot it? So it will be, let us say f1 of ak, and then we have here d k4 delta square by gamma, and I find it the square root of this, okay. So you get something. So now what we get here is that this is should become the data should fall on a line, straight line, and this is the slope of the line. From the slope of the line one can get this particular quantity w by 12 gamma whole to the power half. So that is actually the slope. So from the slope one can get this, therefore the work of adhesion. So one is to do several experiments or several sets of experiments with using delta, different delta, that is the height of the spacer, and measure the A and then scale the result like that and plot it, and one gets this value of the work of adhesion. So, here is such a data that was obtained from the experiment where gamma was taken it to be 20 millijoule per meter square, and after plotting the data, so on data I did not plot, I did not get it for you, but the data after scaling will look something like this. So, several sets of experiments with several value of d, delta, both delta and d also has been done. So, you can vary the d also. Okay. So, this expression takes into account all these properties and even mu also. Okay. So, many cases the adhesive film may have different modulus, but the same surface energy or work of adhesion. So, you take different values of mu, different value of d and all that, okay, and then you can plot the result with this particular slope and like that, and if you use the values of gamma and all that, right values, you get here finally, let us say here you get about work of adhesion comes out to be 45 millijoule per meter square. Now, this value, it so happens for this particular set of surface or the adhesive work of adhesion that matches with the measurement from other experiments. So, on some other experiments also you can do this measurement and you will get the same value of work of adhesion. So, we have shown you, see, remember that in the J-K-R contact mechanics experiment also you can measure work of adhesion, but the J-K-R mechanics is valid only for this elastic half space, okay, where the dimension of this particular adhesive that has not been taken into consideration. So, over here you have a thin layer of adhesive, okay, there you can do a very rigorous way the work of adhesion you can measure, where you take into account the adherence flexibility, the modulus of the film and the thickness of the adhesive film as well. So, you get this approach. So, this measurement is this estimation method is quite rigorous in that manner, right. So, here there is no assumption as such like that, but of course, this works for elastic for a frictionless contact. But if you see my paper, the one that I had cited earlier, from which I am going through all these topics. So, there if you see that this works also in the case where there is friction, okay, there is no slippage, no, there is perfect slippage there. So, that case also, okay, this method will work. So, there will not be much, these coefficients might vary little bit here and there, but it will not be much different. So, that way this is also quite rigorous and robust, okay, this method is also quite robust. So, I will stop here today, and in the next lecture I will continue some more other interesting thing about this particular geometry of adhesion. Thank you.